Swayam Prabha. Digital India. Educated India.
In this session, we will discuss the mechanisms of tissue hypoxia. In the last session, we considered forms in which oxygen is transported in blood and an impaired delivery of oxygen to the tissues or an impaired uptake of the delivered oxygen by tissues can result in tissue hypoxia. VO2 is the notation used to refer to the amount of oxygen consumed by tissues in milliliters of oxygen per minute. Oxygen consumption is denoted by VO2. Now, is there a certain number that we can refer to and say that if VO2 is less than this number, we would then call it tissue hypoxia? We can't put a single number to that because VO2 varies with the metabolic state. Oxygen consumption is lower in resting conditions, and as the metabolism of the body increases, say as in exercise, oxygen consumption will also increase. Let us look at what the oxygen consumption is like at rest in a reference individual and what it is like at maximal or submaximal exercise. So normally in physiology, when we want to refer to some values, we use a reference human being, which is a young adult male of 70 kilograms. When we say cardiac output is 5 liters per minute, it is not in a child, it is not in a woman weighing 50 kilograms, but it is an adult male weighing 70 kilograms. So in such a reference human being, resting oxygen consumption is about 250 milliliters oxygen per minute, whereas at the height of exercise, it can go up manifold, more than 10 times. It can go up to nearly 2.8 to 3 liters of oxygen per minute. So in an individual, in resting conditions, there may not be tissue hypoxia. The oxygen delivery mechanisms may be able to provide the oxygen that is required in resting conditions, but may not be able to provide the oxygen which is required for higher grades of exercise. So in such a person, tissue hypoxia will develop at higher levels of exercise, or we would say that in the resting conditions, the person does not have tissue hypoxia, but there is exercise limitation because the oxygen delivery mechanism is not able to meet with the demands at that level of exercise. We will now see what are the mechanisms which can lead to tissue hypoxia. Prior to that, how did we do those calculations of 250 ml per minute or 3 liters per minute oxygen consumption by tissues? How do we estimate oxygen consumption by tissues? So that would be oxygen delivered per minute minus oxygen returned in venous blood every minute. The difference between the two will give us oxygen consumption by tissues. Oxygen delivery per minute will be arterial oxygen content, which we calculated in the last session, CaO2, multiplied by cardiac output. These two terms alone yield what is called DO2. Some books use that notation for delivery of oxygen. There is no equivalent notation for cardiac output into CvO2. Oxygen delivered minus oxygen returned will give us oxygen consumed. And oxygen returned per minute is cardiac output into venous oxygen content. So that's the equation. Oxygen consumption equals cardiac output into difference between arterial and venous oxygen content. The name given to this is AV oxygen difference. Cardiac output into AV oxygen difference gives us oxygen consumption by tissues in milliliters per minute. We are studying this relationship so as to understand the mechanisms of tissue hypoxia. Now let us start estimating VO2. How do we get arterial oxygen content? We saw in the last session that though arterial oxygen content equals oxygen content in plasma plus oxygen content in hemoglobin. Oxygen content in plasma is negligible. It is oxygen content in hemoglobin that really matters, and to estimate that we need hemoglobin saturation with oxygen, then we need hemoglobin concentration, and then we multiply it with that constant. So 15 into 1.34 ml oxygen per 100 ml blood will give us 20 milliliters of oxygen per 100 ml blood as the arterial oxygen content. The amount carried in plasma is negligible. Similarly, for venous oxygen content, we only have to be worried about oxygen carried in hemoglobin. So that is the expression for venous oxygen content. While SaO2 is measurable non-invasively with a pulse oximeter, SvO2 is not measurable non-invasively. You have to take a venous blood sample, estimate partial pressure of oxygen in that sample, then use the oxygen hemoglobin dissociation curve and see what the saturation is for that PO2. If PO2 is 40 millimeters mercury, oxygen saturation is about 75%. So put that value here, 75% saturation, and then you get 15 milliliters of oxygen per 100 milliliters of blood. So that is arterial oxygen content, and this is venous oxygen content. Arteriovenous oxygen difference is 5 milliliters of oxygen per 100 milliliters of blood, and you multiply that with cardiac output, which is 5000 milliliters per minute. You get 250 ml of oxygen delivered to tissue per minute. This is in the resting state in a reference individual. Calculation of VO2 is one thing, but we are more interested in learning about the pathogenetic mechanisms of tissue hypoxia. Therefore, we will expand these terms and say VO2 is given by cardiac output times CaO2 expanded and venous oxygen content expanded. Then we will regroup these terms. The common terms hemoglobin concentration and 1.34 is taken here, and SaO2 minus SvO2 is given there. This is the form of the equation that will suit our discussions. So now we can understand that any reduction in VO2 or oxygen consumption by cells can occur when there is a decrease in cardiac output, or a decrease in hemoglobin concentration, a decrease in arterial oxygen saturation, or an increase in venous oxygen saturation. When would that occur? When the cells don't extract enough oxygen because of a problem within the cells, then venous oxygen saturation would be higher than normal, reducing the arteriovenous oxygen difference. So these conditions would be cardiac failure. A reduction in cardiac output would be termed cardiac failure. A decrease in hemoglobin concentration would be anemia. A decrease in arterial oxygen saturation would be hypoxia. And an increase in venous oxygen saturation would occur in conditions where there is tissue toxicity, cytotoxicity, or histotoxicity. Now, in these states, it is possible for oxygen consumption to go lower than normal. So, tissue hypoxia in these conditions would be referred as stagnant hypoxia and cardiac failure, because there is not enough blood flow in liters per minute. It is like stagnation, and therefore you call this stagnant hypoxia. If tissue hypoxia develops in cardiac failure, you would call it stagnant hypoxia. If tissue hypoxia develops in anemia, you would call it anemic hypoxia. And if hypoxia in the blood, a low oxygen saturation in blood is what is referred to as hypoxia. If hypoxia in blood leads to reduced oxygen consumption by cells, then you will call it hypoxic hypoxia. We will see later on that in any of these conditions, there will be compensatory mechanisms and oxygen consumption can be maintained normal. Only if the compensatory mechanisms are overwhelmed, the corresponding tissue hypoxia would occur. And this, of course, will inevitably lead to histotoxic hypoxia. These are the 4 conditions which can lead to tissue hypoxia. And it's good to have a mnemonic for that, HASH, for hypoxic, anemic, stagnant, and histotoxic hypoxia. In these conditions, oxygen consumption by cells is reduced. Not only that, oxygen uptake in the lungs will also be low in these 3 conditions especially, because the notation for calculation of oxygen consumption in the lungs is the same. Oxygen consumption equals cardiac output, which tells us how much blood flows through the pulmonary circulation as well, into arteriovenous oxygen difference. How much of oxygen was there in venous blood and how much of oxygen is there in arterial blood. The difference between the two must have come from the lungs. So, we can think of VO2 as oxygen uptake by cells or oxygen uptake in the lungs, because whatever is taken up in the lungs is what is given up in the tissues. In fact, you would come across these equation in a different context in cardiac physiology. One way to calculate cardiac output is to measure the oxygen consumption with a spirometer and divide it by this term. You can actually compute cardiac output. This is one good method to measure cardiac output if you have a spirometer wherein you can measure oxygen consumption. You would learn it as the direct Fick principle for measurement of cardiac output. So, to summarize thus far, a reduced oxygen consumption by the cells can occur in hypoxia, anemia, cardiac failure, and some form of cell injury, tissue toxicity. We did consider the question whether tissue hypoxia would occur inevitably in all these conditions. The answer is it doesn't have to be the case. Only when the compensatory mechanisms in each of these are overwhelmed, then there will be a definitive reduction in oxygen consumed. What are the likely compensatory mechanisms? If we take hypoxia, for example, when there is a reduction in arterial oxygen saturation, AV oxygen difference can still be maintained if the tissues extract enough oxygen from whatever is available. So, venous oxygen saturation can come down. That is one compensatory mechanism. Hemoglobin concentration can increase. The best example is polycythemia of high altitude. People who have been living in high altitude where there is atmospheric hypoxia and therefore the amount of oxygen in blood is less. In those cases, the hypoxic state, the hypoxia in blood, will lead to an increase in erythropoietin secretion, and that will increase red blood cell count and hemoglobin. So, a second compensatory mechanism in hypoxia would be increase in hemoglobin concentration, or there can be an increase in cardiac output. So, with all these compensatory mechanisms, it would be still possible to maintain tissue demands to a large extent, and only if the compensation has failed or the hypoxia is too severe, tissue hypoxia would result. When I say hypoxia alone, I am referring to hypoxia in blood, which is a reduced arterial oxygen saturation. If that leads to tissue hypoxia, then I will call it hypoxic hypoxia. So, do all these conditions always result in tissue hypoxia? No. Tissue hypoxia develops only when the compensatory mechanisms have failed. So, you must appreciate that it is only in hypoxic hypoxia, because oxygen transfer from the lungs is affected, PO2 in plasma is low. Partial pressure of oxygen in plasma is lower than normal, and therefore oxygen saturation of hemoglobin is lower. In these other conditions, because oxygen transfer from the lungs is normal, as shown by the higher color of plasma and red blood cells here, PO2 and oxygen saturation are normal. However, in these two conditions, amount of oxygen carried per minute is lower because there's less hemoglobin here, and in this case, the flow of blood is slower than normal. Cardiac output is lesser than normal. Let us look at this table. In tissue hypoxia, oxygen consumption in milliliters oxygen per minute is reduced. If you look at the arterial oxygen content, it is lower in hypoxic hypoxia and anemic hypoxia because oxygen saturation is lower in hypoxic hypoxia. You know, arterial oxygen content is given by these terms. And our arterial oxygen content is lower due to a low saturation in hypoxic hypoxia and due to a low hemoglobin concentration in anemic hypoxia. Whereas in stagnant hypoxia, arterial oxygen content is normal. It's just that enough of blood does not reach the tissues. Cardiac output is lower in stagnant hypoxia. So when you look at venous oxygen content, because the tissues extract more oxygen from whatever is available, you expect the venous oxygen content to be reduced in the first three conditions: hypoxic, anemic and stagnant hypoxia. I've listed them in that order because it suits the mnemonic hash. When we consider arteriovenous oxygen difference, what can be definitely said is that the difference is lower in histotoxic hypoxia because venous oxygen saturation is higher in that condition. The tissues are not extracting enough oxygen, and whatever oxygen came in the arterial blood is going back in the venous blood unutilized. Therefore, the difference between arterial and venous oxygen is lower in histotoxic hypoxia. It would be higher in anemic hypoxia and stagnant hypoxia. However, when it comes to hypoxic hypoxia, the arteriovenous oxygen difference per se can be normal because both arterial and venous oxygen content have reduced. The difference could be normal. We will see that quantitatively in a while because some of you may be interested in looking at some numbers to understand these phenomena slightly better. So at this level, whatever has to be said about tissue hypoxia has been said. But for some of you who are interested in some numbers, we will extend this discussion and see what are the compensatory mechanisms which work in the different types of hypoxias. An oxygen hemoglobin dissociation curve could be useful in understanding some of these phenomena, and I'd like to convey that properties of hemoglobin itself offers a good degree of protection against tissue hypoxia in hypoxia, that is blood hypoxia. The oxygen hemoglobin dissociation curve has PO2 on the x-axis, which tells you how much dissolved oxygen there is in plasma. And on the y-axis, you can either have oxygen saturation of hemoglobin or oxygen content. You get this axis by multiplying the numbers on this axis by hemoglobin concentration into 1.34. This is the amount of oxygen carried by 1 gram of hemoglobin if it is fully saturated, 1.34 ml oxygen. For example, if you multiply 100% saturation into 15 grams of hemoglobin into 1.34, you get 20 ml of oxygen per 100 ml of blood. that is the right axis, oxygen content in blood. If this represents the arterial point where partial pressure of oxygen in arterial blood is 100, saturation is 100, and oxygen content is 20 ml. And if this represents the venous oxygen point where partial pressure is 40, saturation is 75, and venous oxygen content is 15, then this difference is the arteriovenous oxygen difference, which is 5 ml per 100 ml blood. You multiply that value by the cardiac output, you get 250 milliliters of oxygen consumed per minute. This is at rest in a reference human being who is healthy. Now let us see what happens during exercise in such an individual. The arterial oxygen saturation cannot go more than 100. So that's the arterial oxygen content, but the tissues extract a lot more oxygen and venous oxygen saturation is only 25. And at that, the venous oxygen content is 5 ml per 100 ml blood. Therefore, the difference, which is AV oxygen difference, is 15 ml per 100 ml blood, and you multiply that by the cardiac output to get an oxygen consumption of about 2.2 liters per minute. Let's see what happens in hypoxia. In hypoxia, partial pressure of oxygen in plasma is low. Let us say in this case it is just 60 millimeters mercury. Normally we saw it was 100 millimeters mercury. But because of the way hemoglobin behaves, you notice that hemoglobin is still almost fully saturated. It is almost 95% saturated even when dissolved oxygen is 60 millimeters mercury. Even though there is hypoxia, something wrong with oxygen transfer to blood from lungs, that's what hypoxia is, and therefore you have a low amount of dissolved oxygen, but still hemoglobin is able to soak up as much oxygen as possible and still be 95% saturated. It is still 95% saturated and the arterial oxygen content has not changed much. It was 20 in normal conditions. Even if the hypoxia is as severe as to give a PO2 of just 60 millimeters mercury in arterial blood, arterial oxygen content per se is still 90 milliliters of oxygen per 100 ml blood. So from here, in resting conditions, you just want 5 ml as arteriovenous oxygen difference to meet tissue demands. And therefore, it is enough for venous oxygen saturation to go down to just 70%. You could still have 14 ml as venous oxygen content. In resting conditions, in hypoxia, which is that severe, it is possible to have a normal oxygen consumption. Let us take exercise in hypoxic conditions. I've shown that PO2 in arterial blood is still lower than 60. We will see that later. In exercise, as cardiac output increases, arterial oxygen saturation can actually drop. So let it hover around a little more than 50, and you notice that hemoglobin is still 90% saturated and is carrying a good 18 ml of oxygen per 100 ml blood. And from this, you need about 15 ml per 100 ml for the level of exercise that we considered earlier, where the AV oxygen difference was 15 ml. And if the tissues have to take 15 ml, then the venous PO2 would be about 15 millimeters mercury, giving a 15% saturation of hemoglobin. But then, the tissues have been able to get the oxygen they want. The AV oxygen difference can still be 15 ml, and if the cardiac output is 15 liters per minute, then even during exercise, one can achieve the oxygen that is required by tissues. Now, this is a form of protection that hemoglobin offers against the possibility of hypoxia. A person living in high altitude is able to function normally because, one thing, the behavior of hemoglobin itself protects against possible ill effects of hypoxia. Added to this, other compensatory mechanisms can operate in hypoxia. And what are those? Okay, this is in normal conditions. Those are the numbers we used for exercise. And let us take 75% oxygen saturation in blood. Remember, even when PO2 was 50 millimeters mercury, oxygen saturation was 90. We are talking about even more severe hypoxia in blood, where there is only 75% saturation of hemoglobin. At this saturation, PO2 would be about 40 millimeters mercury. What are the compensatory mechanisms? One, the tissues will extract better and venous oxygen saturation can drop even lower. The prevailing hypoxia, if persisting over a longer period, can induce an increase in hemoglobin concentration. This would take about 1 week to develop. So there can be polycythemia, which protects against hypoxia. Cardiac output can go up, and with all these compensatory mechanisms, it is still possible to maintain an oxygen consumption that is required for exercise. Only if these mechanisms fail, hypoxia per se, which is a reduced oxygen saturation in blood, will lead to hypoxic hypoxia. I hope you're able to make out the difference between these two terms. Only one hypoxia stands with low oxygen saturation in arterial blood. If that results in tissue hypoxia, then we call it hypoxic hypoxia. So there are three compensatory mechanisms that are available to protect against tissue hypoxia in blood hypoxia. Now let us look at cardiac failure. That's a condition where cardiac output is lower than normal. Say this person is not able to have a cardiac output more than 10 liters per minute. There cannot be any change or compensatory increase in arterial oxygen saturation because it is already 100% saturated. Hemoglobin cannot increase either because the signal for erythropoiesis and therefore increase in hemoglobin would be hypoxia. Hypoxia in blood is what stimulates erythropoietin secretion, which will stimulate erythropoiesis. In cardiac failure, because oxygen saturation is normal in arterial blood, we do not expect a compensatory increase in hemoglobin concentration. What can happen is a reduction of venous oxygen saturation, and that's the only compensatory mechanism which could operate in cardiac failure. So in this condition, the oxygen consumption is 1700 milliliters per minute. That can't go any further. So if an individual, as compared to the reference individual who is a 70 kg adult male, if that individual can have a cardiac output of only that much, he will have exercise limitation. He can only do that amount of exercise which is allowable at that kind of oxygen consumption. Now let us look at anemia. In anemia, let us say there's only half the amount of hemoglobin. Cardiac output can go up in this condition. Of course, oxygen saturation in arterial blood is already 100% in normal conditions. Venous oxygen saturation can go down because the tissues are extracting more from whatever is available. And you can achieve an oxygen consumption of about 1750 milliliters of oxygen, and that's the level of exercise that an anemic individual can do. There is exercise limitation as well. However, in resting conditions, there will not be tissue hypoxia because all these these two compensatory mechanisms will take over. So when you play around with these numbers, keep in mind the maximum possible numbers for each of these parameters. Cardiac output, the maximum possible in that 70 kg adult male is about 22 liters per minute. I've said 24 here. In athletes and physically fit individuals who've been training themselves, this can be even higher. It can even be 30 liters per minute. But by and large, in an average 70 kg adult male, the maximum cardiac output that one can reach is about 24 liters per minute. The heart rate can go up to 180 beats per minute, and the stroke volume, remember, stroke volume into heart rate is what gives you cardiac output. Stroke volume can go to 110 ml or 120 ml per beat. The maximum to which hemoglobin can go up is 18 grams per deciliter. This is the number that I find in papers. In fact, this is a number you can find in women living in higher altitudes. They have the highest possible hemoglobin levels. If it goes any higher, it can be problematic because blood will become very viscous and it becomes difficult for the heart to pump viscous blood. There will be impairment of heart function if the blood gets any more viscous. So hemoglobin concentration doesn't go beyond 18 grams per deciliter. That's the maximum for arterial oxygen saturation. Venous oxygen saturation can go as low as 17%. The maximum achievable oxygen consumption is about 3 liters per minute. So if you want to do similar analysis with the oxygen hemoglobin dissociation curve for anemia, then you'll have to change the right axis, because right axis is the left axis into hemoglobin concentration. If it is 15, you will have 20 ml oxygen for 100% saturation. But if it is only 7.5 grams, which is half of that, you will have only half the amount of oxygen that is carried, only 10 ml. Just remember that if you're using the oxygen hemoglobin dissociation curve to understand these phenomena. So if you take anemia in resting conditions, you can go backwards and say in resting conditions, I want 250 ml oxygen per minute. And if the cardiac output is say 5 liters per minute, I want an arteriovenous oxygen difference of 5 ml per minute, going from 10 to 5 ml on the right axis, will tell us that hemoglobin will be 50% saturated in venous blood. Thank you for your attention.